Hey y'all, welcome to 3.3. In this lesson, we are going to look at writing equations from rational functions. And so we're going backwards from what we've been doing the last couple lessons. Instead of starting with the equation, we're going to start with either a graph or we're going to start with some of the features of the graph. And from there, we'll write the equation. So, little review. In this warm-up, graphing this equation, you see factored form. In the numerator, it's a sum of cubes, so it is factored by that formula. In the denominator, we found magic numbers, and we notice here that those x plus 2 factors will divide each other out. And so simplified factored form would be x squared minus 2x plus 4 all over x minus 1. So because we did have a factor that divided out, we do have a whole. And to find that whole, we take that x plus 2 that divided out, set it equal to 0, and proceed to solve. So that x value is negative 2. To find the y value, we plug into that simplified factored form. So negative 2 squared minus 2 times negative 2 plus 4 all over negative 2 minus 1. That ends up being 4 plus 4 plus 4 all over negative 3, which is 12 over negative 3, which equals negative 4. So our whole is at negative 2, negative 4. So on the graph, negative 2, 1, 2, 3, negative 4. Here is a whole. It's not a great spot. Here is the whole at negative 2, negative 4. So that space there will be a whole. Now, let's talk about roots. Roots are solutions to the numerator. We already know that this will not factor anymore because it was a difference of cubes and it was factored. So what we'll need to do is something different. We'll need to use the quadratic formula here. So to solve with that quadratic formula, a is 1, b is negative 2, c is 4. Remember, we never plug x's into the quadratic formula. Only constants. Only the coefficients. So, solving x equals negative b, which is 2, plus or minus the square root of b squared, so negative 2 squared, minus 4ac, so 4 times 1 times 4, all over 2a, so 2 times 1. So that is 2 plus or minus the square root of 4 minus 16 all over 2. So then that's 2 plus or minus the square root of negative 12 all over 2. And that negative under the square root means our solutions are not real. They are imaginary. That means the graph does not cross the x-axis. So we actually have no roots. The graph will not cross the x-axis. For vertical asymptotes, take the denominator, x minus 1, set it equal to 0, and solve. So we will have a vertical asymptote at x equals 1. So the graph will not cross that line. And we have a vertical asymptote. For tangent and together, we look for any factors that were squared. There are no factors that were squared here. So there are none. For end behavior, we look at the degree of each piece. I like to look at the original in order to do that. So in the numerator, we have a degree of 3. The denominator, we have a degree of 2. That is a high over low. That means we are going to have a slant asymptote. We need to find that equation. To find that equation, we divide. Now, we'll need to use the simplified form to divide, and that's a little bit of a bonus because it lets us use synthetic division. So our coefficients are 1, -2, and 4. We're dividing by x minus 1, so we put a positive 1 on the outside. Then to do that synthetic division, we bring down the first 1, and we multiply around the corner. 1 times 1 is 1. Add, we get -1. Multiply again, -1. Add, we get 3. 3 is the remainder, which on slant asymptotes only, we ignore. -1 is a constant. 1 is the x coefficient. So that slant asymptote is y equals x minus 1. It's the graph y equals x minus 1. So to graph that line, its y-intercept is -1, has a slope of 1, so up 1, right 1. And down 1, left 1. That hole's in the wrong spot. I'll fix it. So there's our line. And back to this hole that I could not get in the right spot. It's at -2, -1, 2, 3, 4. So this is where that hole should have actually been. I had it a little off. Sorry about that. So let's check y-intercept. And that y-intercept is always when x is equal to 0. And again, if you'll go to the original function, everything within x zeroes out. So that leaves us with 8 over -2 or -4. So that y-intercept is 0, -4. So here's our y-intercept. Now, to actually sketch this graph, we need to connect the points we have in the same sections, and we need to follow the asymptotes. The hole is the furthest thing on the left. So from the hole to the left, it has to follow that end behavior, follow that slant asymptote. It does have to cross the y-axis at the point indicated. So it's going to go up a little bit, then cross that y-axis. It's heading down at this point, so it does need to keep going down. Really need to make that look like it crosses the axis. And it goes down towards that vertical asymptote. So there's one piece of the graph. Now, the other piece of the graph is on the other side of that asymptote. And because there is not a together, there's not a together on opposite sides of the vertical asymptote, the graph goes opposite directions. So on the left of that asymptote, it went down. So on the right of the asymptote, it has to go up. So our other piece of the graph is here. There was not a together, so it went the opposite way on each side of the asymptote. Now, for the domain, it's holes as well as vertical asymptotes. That break up domains. Holes and vertical asymptotes break up domains. So this domain starts at negative infinity. It goes to the x value of the whole, -2. Start over again with -2. We go to the y-intercept, which is 1. Start over again at 1. And we go to infinity. So there is your domain. Now, that is our graph. That is the graph of all the parts. Now, a few other questions. We want to use the interval for values of x such that f of x is greater than 0. Think of that as y being greater than 0. If y is greater than 0, we are above the x-axis. And above the x-axis, where the graph exists, is this piece over here. So that piece's domain is from 1 to infinity. We do not include the 1 because that was a vertical asymptote. Now, something that we saw before on different types of graphs are the limits. And so if we look at each of these limits, we can figure out where those are. So remember, this notation means the limit of f of x as x approaches -2 from the left. Another way to phrase that is, what are the y values approaching? Near holes and asymptotes and at the far ends of the graph, the end behaviors. So in this case, limit as x approaches -2 on the left. So look at what's going on at -2. At x equals -2, there is a hole. So we are looking at what the y's are doing close to the hole. Well, our hole is at -2, -4. So close to that hole, the y values get really close to that y value of -4. They can't touch -4 because that's a hole, but they get very, very close to that value of -4 on the left side and on the right side of that hole. The y values are both approaching that -4. So the limit on both sides of that hole, the left and the right, are both -4. Okay, and both of those are the y value, the y coordinate. Let me change that to coordinate. That is the y coordinate of the hole. On either side of a hole, the limit approaches the y value of that hole. Now, let's look at what's going on at the next limit. The limit as x approaches -1 on the left, that negative power meaning on the left. X equals -1 is a vertical asymptote. So if we look at what's going on at the vertical asymptote, if we label that graph left and right, left, right, on top, on the left, there's nothing. If we go to the bottom, left side, right side of that vertical asymptote, we see the graph does exist on the left and it is going down. So on the left of that asymptote, the graph is approaching -infinity because it is going down. On the right of that graph, that plus sign looking like an exponent means on the right side. If we look at the graph on the right side of the asymptote, the graph was going up. So that y here approaches positive infinity. And remember, at a vertical asymptote, that f of x will always approach either plus or minus infinity, because that's what the vertical asymptote is making the graph do. Then this last limit is asking us about the limit as x approaches negative infinity. Negative infinity, x approaching, is the far, far left of the graph. So if we look at the very left edge of the graph, we are following that slant asymptote. So we are going to negative infinity here. And then on the other side, the limit as x approaches positive infinity. That is the far right edge of the graph. And if we look at that far right edge of the graph, we're again following that slant asymptote, which on that side is going up. So we will be going here to positive infinity. And there are your limits there. As x approaches either positive or negative infinity, the y will approach whatever that end behavior indicated. Sometimes it might be a horizontal asymptote. Sometimes it may be a slant asymptote. Now, what we want to do from here is flip this around just a little bit. We want to use the information about the function to write its equation in factored form. So, looking at the information in example 1, if we have a whole at x equals 3, a whole means the factor was in the numerator and the denominator. And if x equals 3, no, I didn't want you. If x equals 3, that means the factor that was used had to be x minus 3. And that had to be in both the numerator and the denominator. If we have roots at -7, 0 and at 0, 0, roots come from solving the numerator. So if a root is at x equals -7, that means x plus 7 was a factor. If a root was at x equals 0, that means x was a factor. Then let's look at asymptotes. Asymptotes, it says, come together at x equals 2. And we have vertical asymptotes at x equals 2 and x equals 6. Vertical asymptotes are all from the denominator. So if x equals 2 was an asymptote, x minus 2 was a factor. It told us we had a together at that asymptote. That means that factor is squared. Then we have our other asymptote at x equaling 6. So x minus 6 was our factor. And the very last thing it gives us was the end behavior at y equals 0. It's a horizontal asymptote because y equals 0 is the horizontal line. So if we look at the degree in the numerator and the denominator, we can compare those and see if that works or see if we need to adjust anything in our equation. We have in the numerator an x, an x, an x. So that's a degree of 3. In the denominator, we have an x that's squared, and an x, that's a degree of 4. So that is a low over high. And from our mathematical poetry about in behavior, low over high, 0 equals y. So yes, there's a horizontal asymptote at y equals 0. So here is our equation. We take the parts, I knew that was going to happen. We take the parts of the graph that were given. I don't know why I want those erased, but I really do. Thank you. Okay, so we take the parts of the equation and we put them in place. So let's try this again. Let's look at example 2. Tells us we have a hole at x equals 1. Holes are in the numerator and the denominator. So that means x minus 1 is in both the numerator and the denominator. Roots at 2, 0 and negative 8, 0. Roots are in the numerator. So x minus 2 and x plus 8 are factors in the numerator. We have a tangent root at negative 8, 0. So that root gets squared. We have vertical asymptotes at x equals 9 and x equals 6. Vertical asymptotes are in the denominator. So that would be x minus 9 and x minus 6 in the denominator. And it gives us the end behavior being a slant. So let's talk about the degree. X squared. So that is a degree of 4. In the denominator, x times x times x is a degree of 3. So that is a high over low. And our poetry does say that that is a slant. So we don't need to adjust anything to give that a slant. And here is our equation. So, the other part of this idea is that we look at a graph and we find the equation from the graph. So, all those pieces that we've been finding in order to draw the graph, reverse that, look for them, and put the equation together from there. So, if we look at this graph, we see no holes. So we don't need to do anything there. We do have some roots. We have a root at negative 4, 0. And we have another root at 2, 0. So that means x plus 4 and x minus 2 are in the numerator. Then look for vertical asymptotes. Look for vertical asymptotes, and we do have 2 of them. They are at x equaling negative 1 and x equaling 6. So those factors are in the denominator. So x plus 1 times x minus 6 is in the denominator. We need to look at the end behavior. And the end behavior is a horizontal asymptote right here at y equals 3. So to get a horizontal asymptote that's not at 0, the degrees would have to be the same. And the coefficient game equaled 3 over 1. Meaning we need a 3 as the coefficient in the numerator so that the lead coefficients divide out to be 3 over 1. So here is our equation. Now, let's talk about these limits. We are looking at the limit as x approaches -1 on the left. So this vertical asymptote at -1, left, right. On the left, up top, we see nothing. The left on the bottom, we see the graph is going down. So that's a negative infinity on the left side. On the right side of that vertical asymptote, there is the graph on the top, and it goes up. So it goes up to positive infinity. Looking at the other vertical asymptote, left, right, left, right. On the left, we see nothing up top, but we do see graph on the right, on the left, on the bottom, sorry. On the left, on the bottom, and it's going down, negative infinity. On the right, the graph is going up, so that's a limit of positive infinity. Then if we look at the far left and far right, the graph, so as x approaches negative infinity, it's the far left of the graph. On the far left of the graph, it's approaching the end behavior. And that end behavior here is that asymptote horizontal, y equals 3. So that limit is 3. Same thing on the far right. The far right of the graph, we're approaching the end behavior. So that is 3. And there are your limits. So let's try another one. Let's look at example 4. Go through all the pieces. Look for anything that may be there. So looking at all 3 sections of that graph, there's no holes. So no factors divided out. We have roots. We have roots at -3, 0, at 1, 0, and at 2, 0. Just look really carefully all along that x-axis. So that means x plus 3, x minus 1 times x minus 2 are all factors in the numerator. None of those roots bounce, have a tangent, so none of those are squared. Let's look at vertical asymptotes. We have a vertical asymptote here at x equals -2. And another one at x equals 3. Those factors go in the denominator. So that means that x plus 2 times x minus 3 is in the denominator. If we check out the end behavior, the end behavior is a slant. To have a slant asymptote, we needed a high over low. For slant, we go. So in the numerator, we have a degree of 1, 2, 3. And in the denominator, we have a degree of 1, 2. That is a high over low. So our end behavior checks out. And here is the equation of that line, that curve, sorry. Now, let's look at its limits. As x approaches -2 on the left. So if we look at this asymptote at -2, left side, right side, left side, right side. On the left, the graph is going up. It's a positive infinity. On the right, there's nothing on the top. That graph is going down on the right, so that's a negative infinity. If we look at the next asymptote as x approaches 3, left side, right side, left side, right side. Up top on the left, there's nothing. On the left, the graph is on the bottom. going down. So on the left, that goes to negative infinity. On the right, the graph is up top and it's going up. So it's going to positive infinity. Then if we look at the far left and far right, that was a right. If we look at the far left and far right of the graph, on the far left, we're over here following that end behavior, which is a slant going down. So that's a negative infinity. On the far right of the graph, we're again following that end behavior, that slant. So we're going to positive infinity. And there are the limits. So let's take a look at these last couple. On the writing the equation, we have roots at -1, 0, 2, 0, and 3, 0. The tangent root at 3, 0. All of that goes in the numerator. So we have x plus 1, x minus 2, x minus 3 in the numerator. The tangent root at 3, 0 means that x minus 3 factor is squared. We have a vertical asymptote, it tells us, at x equals 4. That's in the denominator. So x minus 4 is a factor in the denominator. The end behavior is a slant. The degree in the numerator is 4. X times x squared. And the degree in the denominator is 1, only 1 power of x. So that is a high over low, which does make a slant. So nothing else needs to be done here. This is your equation. Let's do that a little better. There is your equation. And let's take a look at this very last one. We are writing the equation of the function, so we need to find all of the pieces. If we look, we do have a hole. We do have a hole. In that middle piece below the axis, we do have a hole. We have a hole at x equals 3. That's in the numerator and the denominator. So x minus 3 is a factor in both places. And then we look at roots. And if we look at the x-axis, we do cross that x-axis at 0. 0, 0, and it is a tangent root. It does not go through the axis. It hits the axis and bounces back. That is a tangent root. That means x was a factor in the numerator, and because it's tangent, it's squared. For the vertical asymptotes, we have a vertical asymptote at x equals -4 and another vertical asymptote at x equals +4. So x plus 4 times x minus 4 are factors in that denominator. And then if we look at the end behavior, I did not write those down. Let me do that for consistency here. We had a vertical asymptote at x equals -4 and at x equals 4. Neither one of those were togethers, so they are opposite directions. So there's no squaring in those asymptote factors. And now we need to look at the end behavior. The end behavior on this is a horizontal asymptote at y equaling 4. To get a horizontal asymptote, the degrees had to be equal. In the numerator, we have an x squared. So that's a degree of 3. In the denominator, we have x times x times x. So that is a degree of 3. So those degrees being the same, we play the coefficient game, which means those coefficients need to divide out to be 4 over 1. And so we need a coefficient of 4 in the numerator. So there's our coefficient of 4. And here is the equation of the graph.